Today we're going to look at transformations of graphs. Transformations of graph is essentially where you take one of your basic library of function types and you do things to your function to move it around in your graphing plane. So moving it up, down, left, right, stretching or shrinking it either vertically or horizontally, or even potentially reflecting it over the x or the y axis. And what we're going to see, we'll practice all of our transformations, but we'll see that learning these transformations is very helpful because it speeds up our graphing process. We can graph things a lot more easily when knowing these transformations, and it also allows us to design our graphs to have certain behavior in terms of the equation as well. The first transformation we're going to look at are vertical shifts. So this is going to be shifts on our graph either going up or down. So what I first want to start with is graphing what we call the parent function. And the parent function is of the same type of the function that you wish to graph. So for instance, here we all have functions of the type x squared, or our squared function. And so I want to graph essentially the parent function, which is the same function without any other operations happening on it. There's nothing, no behavior that's happening other than just the behavior of my graph, which is squaring. So the parent function, we'll go ahead and graph first to get a sense of some key points on my graph. So for x squared, I've already built our table. So when x is -2, when you square it, you get 4. So I'll plot that point on my graph. When I take -1 and square it, I get 1, which will be another point on my graph. 0 squared yields 0. 1 squared yields 1. And 2 squared yields 4. So these 5 points that I just graphed, those are going to be kind of key points that show the shape of my parent function. So for an x squared function, our shape is a parabola. So let me go ahead and connect these points. So here's our parabola or U shape that is characteristic of anything that has your variable x being squared. And because we will write multiple graphs on the same graphing plane, it's helpful to label them, and you can label them with the letter that represents your function. So this is my parent function, f of x. Now from this parent function, I want to go ahead and graph some other functions. The first one is going to be x squared minus 4. And so I can take my table values and plug them in here. We can always graph using a table. And hopefully what we'll notice is that there's a certain behavior that's going to reveal itself and will help show what that transformation of -4 does to our parent function. So when I put in -2 and square it, we know we got 4. Then I would subtract 4. So 4 take away 4 gets me 0. So at -2, now I'm at 0. For -1, when we squared it, we got 1. Minus 4 gets me -3. The next point at 0, we square it, you get 0. Subtract 4 gets you -4. So that's a point 0, -4. Then my next point, 1 squared is 1, minus 4 gets me -3 again. And 2 squared gets me 4, minus 4 gets me 0. So what we can see, if we look at our point values in the table, of course they're 4 less than the y-coordinates from our parent function. And we can also see on the points as we graph them that all of these points, for the same x value points on the parent function, they got moved down 1, 2, 3, 4 spaces, right? Pretty consistently. If you count from one of those parent function points down 4 places, you can generate the same dots that we just got from our table. So what this -4 is going to do is this is going to take my parent function and move it down those 4 units. And that should make sense. Our x squared is yielding our y value. When we subtract 4, that pushes that y value 4 units less. So that would make our graph go 4 units down on our graphing plane. So let me go ahead and draw the parabola. That's our function g. And then our last function, we want to take our squared parent function and add 2 this time around. So we're taking all of the squared values, so 4 if you add 2 to that gets you 6, 1 if you add 2 gets you to 3, 0 add 2 gets you to 2, 1 added with 2 is 3, and 4 added to 2 is 6. Now if we plot those, so -4, here I'm at 6, -1 I'm at 3, 0 I'm at 2, and 1 I'm at 3, and 2 I'm at 6. We can see that same parabola shape. However, this time around, if I compare them to the parent function graph for the same x value point, now I'm 2 units more than, or 2 units above where my parent function was. So kind of like what we saw on the last graph, we took our y values and added 2 units. On our graph, that would move it up 2 units from where it was on my parent function. So what does that tell us then in general, right? If I'm working with not just the x squared parent function, but some other parent function from our library of functions, what would happen? Well, in general, if you have some parent function f of x, and you add some constant number k, after your parent function has occurred, right? So we can see our x squared was our parent function, then we added or subtracted our values. When it's happening outside your parent function, that's going to be an indicator it's that vertical shift. So adding a number will shift it upward, whatever that k value is in units. So when we added 2, it moved it up 2 units. Subtracting a value after my parent function has occurred is going to shift it down a particular value of units. So for instance, on our example, we had our g of s function be our parent function minus 4. So that shifted it down 4 units. So that's how we can know how vertical transformations are going to change our parent function. So you would see your parent function, if you subtract a number, it will push it down, add a number, it will push it up. And so we can use that to graph our functions a lot more quickly. I wouldn't necessarily have to graph all the values in the table. I could just take key points from my parent graph and do that shifting process of up or down. And it also lets me, in some instances, when I see a graph in my graphing plane, more easily generate the equation that yields that graph. The second graph transformation we're going to talk about is horizontal shifts. And horizontal shifts are going to be movement horizontally, so that could be to the left or to the right. For this particular example, we're actually going to work with the parent function absolute value of x. So I've plotted some values in the table for that function. So when we take the absolute value of -3, you get the positive result of 3. Absolute value -2 gets you 2. -1 gets you 1, and so on. So I'll go ahead and plot these numbers and show my parent function graph. And so if I ever see an absolute value, I would know to generate this sort of parent function graph, that it's this kind of V, sharp V shaped graph. So now let's go ahead and take a look at these changes that we've made. So in the first graph, our function g, we want to take our parent function, absolute value of x, but within my absolute value bars, instead of x, I'm putting x plus 2. So let's see what that actually does to our point value. So when x is 3, I would put in -3, so -3 would get added with 2, so that's -1. When we take the absolute value of that -1, I get a 1 out of it. Then we would calculate it for 2, so if I replace x with -2, you would get -2 added with 2, which is 0. We then take the absolute value, and that yields a 0. For -1, we would replace x with -1. When you add it with 2, you get a positive 1. And the absolute value of that positive 1 is a positive 1 again. For 0, if we replace 0 for x, added with 2 gets me 2. Take the absolute value of 2, and you get 2 again. Replacing x with 1, added with 2 gets me 3. Absolute value of 3 is 3. Replacing x with 2, you get 2 plus 2, which is 4. Absolute value of that is 4. So what we're noticing, hopefully, is I do have some of the same values as my original parent function, Specifically this 1, 0, 1, 2, I can see is also occurring for my y values. However, they're happening for lower values of x, right? When I first got this 1, it happened when x was a -1, but now that value of a y value of 1 is happening when x is -3. So we're seeing the same numbers, but they're happening for lower values of x. So let's see what that would look like on our graph. So when I graph -3, 1, -2, 0, -1, 1, 0, 2, 1, 3, and 2, 4, I can still see that characteristic V shape for the absolute value. However, compared to my original parent function, it's now to the left of where my parent function used to be. And we can see how many units got moved to the left by comparing similar points. So if I use like what we call the vertex, the tip of the V, it used to be at 0, 0, now it's at 2, 0. So my entire graph, every single key point got shifted to the left 2 units. And we could kind of see why that happened, right? As we were plugging in those values, I was adding 2 to all of my x's. And so that actually changed my output for y, and essentially increased my value of y by 2. So really it's kind of counterintuitive. When I first looked at this, maybe I would think that that +2 would move it to the right 2. But really, because of the nature of this 2 affecting my x before my parent function, it's actually the opposite. So that +2 is going to move all of our parent function values to the left 2 units. So one way you can remember that, and how I remember that, is I remember that it is that counterintuitive piece, that it's really kind of the opposite of what we'd expect. When I see +2, I would think that it moves to the right, but it's the opposite. In reality, it moves to the left. Let's see if that would hold true for the second one, right? If it follows the same sort of pattern, I see -1, so maybe in my head I would think that moves it to the left, and we know that that isn't the case, right? The addition adds it to the left, so this minus might make me think that it is also counterintuitive, that it'd move it to the right 1 unit. And let's see if that's right. Let's see if I plug in these x values into my h of x function and see if it really does move my values that direction. So if I plug in -3 as my value of x, -3 minus 1 is -4. You take the absolute value of that and you get a +4. If you plug in -2, take away 1 gets you -3. The absolute value will make that +3. When I put in -1 and subtract 1, I get -2. Its absolute value is 2. 0 take away 1 is -1. Its absolute value is 1. When I put in 1, 1 minus 1 is 0, which yields an absolute value of 0. And 2 minus 1 is 1. The absolute value of 1 is 1 again. So I can see, if I look at my y values, I still do have the same y values as my original function, right? I can see the 1, 0, 1, 2, 1, 0, 1, 2. However, they're happening later now, right, for bigger values of x. So what would that look like on my graph? Is it really that movement right that we were expecting? So at -3, I'm at 4. At -2, I'm at 3. -1, I'm at 2. At 0, I'm at 1. At 1, I'm at 0. And 2, I'm at 1. And when I graph this, I can actually see for those key values on my parent function, for instance the 0, 0, is really 1 unit to the right. So it does fit that pattern that we were expecting, that when you're changing the value of your x, right, you're adding or subtracting a value to x within your parent function, it's going to move it left or right in a very counterintuitive way. So adding to the x will move it to the left, subtracting on your x will move it to the right. So let's write that as our rules. So if I replace x with x minus some h, where h is a constant, we know that subtraction piece will actually move it to the right, whatever that h quantity of units is. If I add, right, if I do x plus h within my parent function, that's going to move it to the left. So that's how we can shift our graph left and right within our graphing plane, is we're going to be changing our x to a value of x plus or minus some constant number. Our next transformation is an interesting one, and this is where the actual shape of our graph is going to get changed a little bit. In our previous two transformations, we were really taking our graph like a rigid shape that was then just getting shifted in our graphing plane. We either pushed it up vertically or pushed it down vertically, moved it left or to the right horizontally. Now we're going to actually change the shape a little bit and make it look maybe more stretched out or compressed. In this case, in the vertical direction. So we're going to be looking at our values changing vertically, or really the values of the y changing, since that's our vertical variable. So let's start with our parent function. Our parent function is the x squared function. So I've plotted some values of my x squared function. Sometimes you may get values that fall, outside of your graph, and that's fine. You don't necessarily have to graph those points. So negative 3, 9 falls off my graph. I won't graph that. But negative 2, 4, I could put as a point on my graph, so I will do that. Negative 1, 1, 0, 0, 1, 1, 2, 4, and 3, 9 also falls off my graph, so I won't graph that. But we'll see why I included those additional points in a little bit here. So now this is my parent function, my squared function f, and we want to go ahead and graph these transform functions. So the function g is still my parent function, it's x squared, but outside of my parent function I want to multiply by 2. So this is an indicator why, we'll talk about horizontal stretches and compressions, but this is why it's a vertical stretch. Anything that happens vertically is going to happen outside of your parent function, kind of like how we added and subtracted a number outside, boosted it up or down. Now I'm multiplying a number on the outside. So again, it's outside my parent function. That's going to be a vertical change. When you're doing math on the inside of your parent function where x is, that's going to be a horizontal change. So like when we added or subtracted a value to x, like in our last example, that created a horizontal movement in my graph. When we get to our fourth exploration, we'll see how multiplying a number inside where x is can also make some horizontal changes. So let's first start with this g of x. So I'm multiplying that 2 on the outside, so I know it's a vertical change. And so what would this do? Well, I would still, input my value as x, so like I would square my 3 and get 9, and then that 9 would get multiplied by 2, which gets me 18. So really what's happening is I'm taking kind of all these y values I had on my parent function, and those are getting multiplied by 2, right? So when I squared negative 2, it gets me 4. You multiply that by 2, it gets you 8. 1 squared got me 1. Multiply that by 2, you get 2. 0 squared is 0. Gets multiplied by 2, which is 0. 1 squared gets you 1. Multiply that by 2, you get 2. 2 squared is 4. Multiply that by 2, which is 8. And 3 squared is 9. Multiplied by 2 is 18. So we can see we still have kind of the same basic shape of our squared values like what we had in our parent function, but now they're just all bigger. Right? So let's see what that looks like on my graph. So 218 or 318 I can't graph, that falls off my graph. 2,8 also kind of falls off my graph, although I can envision kind of where that would be above my graph. Negative 1, 2 I could definitely graph. 0, 0, and 1, 2. So I know I'm going to have that same parabola shape, and it's just going to increase a lot more quickly, right? So it's going to look something like that. Now what would we call that? So it's the same basic parabola shape. It didn't move anywhere in my graphing plane. However, all my y values are now twice as big as they used to be. So what we call that is a vertical stretch. And one way to think of that is if I had grabbed on to, say, the vertex, the 0, 0 point, and then the two ends of my graph where the zeros are, and then I vertically stretched it, up and down, my graph would stretch and create that like elongated looking green graph that we created. So that's what a vertical stretch is. Like imagine you took the lowest point and highest points of your graph, and then moved your hands apart from each other, upward and downward, to create that stretch. So we would say for this one that it's a vertical stretch. And we often want to state by how much. It's a vertical stretch by 2, right? Because we multiplied by 2 to create that stretch behavior. The next graph, h, is very similar. I'm multiplying outside my parent function, but this time I'm multiplying by 1/3. So let's see what would happen there. So again, I'm getting the same squared values, right? -3 squared gets me 9. But then I'm going to multiply it by 1/3. And multiplying by 1/3 is really mathematically the same as dividing by 3. So 9 divided by 3 gets you 3. So we can see why I had that point there, right? It gets me a nice output. Then 2 squared gets me 4. That divided by 3 gets me 4/3, or 1 1/3. 1 squared gets me 1 times 1/3, leaves 1/3. 0 squared is 0, times 1/3 is still 0. 1 squared again is 1, times 1/3 gets you that 1/3 again. 2 squared is 4, times 1/3 gets you the 4/3. And 3 squared is 9, times the 1/3 gets you 3. So similar to our last one, we're getting that same scoring behavior with seeing those repeated values kind of for y. However, they're much smaller than what they were on the original parent function. In fact, they're 1/3 as big as they used to be. So what would that look for my graph? So at -3, I would be at 3. At -2, I'd be about 1 1/3. So I'd kind of eyeball that on my graph. -1, I'd be at 1/3, also kind of eyeballing it. 0 0, 1 1/3, 2 4/3, and 3 3. So I still have that parabola shape, but this time around it looks a lot wider, right? Because my values are not increasing as quickly as they were compared to my parent function. And so what do we call that? Well, in a case like this, we're decreasing our y values by 1/3. So we think of this as what we call vertical compression. So how can we visualize that? So what you could think of is if you took your black parent function graph, right, and you grabbed it at the vertex and grabbed it where the 2 arrows are, and this time instead of pulling your hands apart, if you pushed your 2 hands towards each other, towards the middle, right, what would end up happening is our graph gets wider, right, as it gets squished together. And that's really what's happening here, is we're decreasing our y values, and so they're becoming smaller, and our graph is getting wider as a result. So we would consider this vertical compression by 3. I know you see the 1/3 there. However, the overall effect is it's 3 times less than what it used to be for y. So that's why we say it's a factor of 3. Then the last graph I want to look at is, what if the number that I'm multiplying outside my parent function is a negative number? So here I'm just going to keep it a -1, but it could be other negative values, -2, -1/3, negative whatever. We're multiplying a negative value. That's going to create a vertical change. So what would it do? Well, we'd still have all of our squared values, but they would get multiplied by a -1. So my 9 would become a -9. The 4 would become a -4. 1 becomes a -1. 0 doesn't change sign. 1 goes to -1, 4 goes to -4, 9 goes to -9. And then we can graph that. So 2, -4, -1, -1, 0, 0, 1, 1, 2, 4. So we can, again, see that parabola shape still. However, it's not opening upward anymore. Now it's opening downward. And so what this -1 multiplier did to our graph is it reflected it over the x-axis, right? So it reflected all of those y values essentially by making them negative, right? What used to have been positive y values are now negative y values. So a negative multiplier does still change it vertically, right? It's changing our y values into negatives, and as a result it becomes that reflection over the x-axis. So if we go ahead and go through our rules here, when we're multiplying a number outside your parent function, that's going to be a vertical change. When that number is greater than 1, right? That's what we mean by that A. That A is a multiplier. So like in the instance of when we multiplied by 2, right? 2 is greater than 1. When your multiplier is greater than 1, that's going to be that vertical stretch. By whatever that A value is. So when our A was 2, it was a vertical stretch by 2. If my multiplier is between 0 and 1, like our 1/3 example was between 0 and 1, that's going to be that vertical compression. And we state what it's being compressed by the bottom value. So it's a compression by 3 in the values that we have here. And then the last part is our reflection. So when I have that negative outside my parent function, like a -1 multiplier, that's what's going to reflect it over the x-axis. All right, so now we're going to go ahead and take a look at our horizontal stretches and compression. So what are some of the key things that we can notice different compared to our vertical stretch and compression? Well, we can notice where our multipliers are happening. So this time around, my parent function is the square root of x, and my multipliers are happening inside my parent function right on the x. So whenever anything's happening right on x, that's a horizontal change. So we're going to see changes in our x values here. So let's go ahead and graph our parent function to start. So I included some extra values here that don't generate any points on my graph, because you cannot square root a negative number and get a real number as a result. So when x is -4, -2, -1, those won't be points on my graph. Where I start having values is at 0. So 0, 0 is the first point on my square root graph. Then the square root of 1 is 1. Square root of 4 is 2. And so we get this kind of half of a parabola sort of shape for that square root function. Now let's go ahead and graph all the rest of these. So the first graph we're going to look at is going to be the 3 times x within my square root graph. And so let's see what that does to our values. So I'm first going to try the values in the table, and then we'll see what kind of the result looks like and if that matches what we were expecting. So I can't plug in -4, -2, -1. All those would multiply by 3 and still yield a negative number. So none of those would be real. So I don't graph those as points. At 0, 3 times 0 gets me 0. When I square root that value of 0, I still get 0. At 1, I'm starting to see some different numbers. So 3 times 1 is 3. And then the square root of 3 would be the result there. Now the square root of 3 is difficult to graph without actually knowing its value, so it may be worthwhile to actually figure out what that number is in the decimal form. So let's actually figure that out. So if I do square root of 3, it's about 1.7. So this is about 1.7. And then for a value of 4, I get 3 times 4, that's 12, which would be square rooted. And the square root of 12 is, again, similar to square root of 3. I could reduce it, but that doesn't really help me better understand the value. So typing it into the calculator to get my decimal approximation is going to help me graph this. So the square root of 12 is about 3.5. So let's graph the points that we can here. So 0, 0 is a point on my graph. At 1, I'm at 1.7. So we'll do our best to kind of approximate that. And at 4, I'm at 3.5. So we can see my graph is getting bigger y values than what it did before. Right? My values of y are larger. And we would probably go, oh, that's a vertical stretch. And in a way it is. Our horizontal stretches and compressions also look on our graphs just like the vertical ones. And really the only difference in how we can tell them apart is our equation. and the fact that my 3 is happening inside on x, that's what really makes it that horizontal change. So if I think of this horizontally, right, what would be happening to my graph? Well, if I took kind of the 0, 0 point on my graph and then where my arrow is, to make it go up, I wouldn't be stretching or pushing my hands apart, right? If I pulled my hands apart, that would make my square root graph become more flat and perhaps kind of get stretched towards the x-axis. So it's not a stretch. So what would I need to do then? Well, if I can't put my hands apart, I can pull them together. So if I put those two ends of the graph together, then we can see this curvature would get smushed, right, and kind of go up. So here we would actually call this a horizontal compression. And how we designate that compression, what we're going to find out later in our notes, is we actually do 1 divided by whatever your multiplier is within your parent function. So here it's a 3, so I would say by 1/3. Right? So it's kind of funny that we use the fractional values, but again, this is just to be in contrast with our vertical stretches and compression. So the horizontal compression would be the first one that we see. Let's look at the next graph here. So the next graph, now I am multiplying by 1/2 within my square root. So if we pick our values, so -4, -2, -1, those all still don't work. Right? Those are not going to yield real values for us, so we can't actually graph them. At 0, if I plug in my value of x is 0, I get 0 times 1/2, which is 0. If you square root 0, you still have 0. At 1, right, I have 1 times 1/2, which is the square root of 1/2. And that one, again, we'd want to know the decimal approximation to get a sense of what that value is. 0.7, about 0.7. Then my last number, if I put in 4, 1/2 of 4, or 1/2 times 4 is 2, and so we'd look at what our value is at the square root of 2. So for square root of 2, that's about 1.4. And so let's graph those. So 0, I'm still at 0. 1, now I'm at 0.7. And 4, I'm at 1.4. So we can see that our numbers went down for y, right? We're getting smaller values of y. And my graph also looks a lot more flat, right? It's a lot closer to the x-axis compared to my original parent function. So kind of like we mentioned on the last one, I would think of taking my black parent function and grabbing it at 0, 0 and grabbing it at my arrow and thinking of moving my hands apart to be a stretch or putting my hands together to create a compression. So we said G happened because I put my hands together, right, and created a compression. So how would I elongate to create the red graph? Well, I would need to move my hands apart, right? I'd have to move them apart to create that. So this is actually a horizontal stretch. And we'd want to talk about how we're stretching it, by how much. And so it's similar to what we saw before, that we're going to do division of our factor. So 1/2, it would be 1 divided by 1/2. And so that overall we think of that as a value of 2, right? So it'd be a horizontal stretch by 2 here. And more than saying how much it's a horizontal stretch or compression by, that number is not as important, I'd say, as classifying the type of relationship. So if you see a number bigger than 1 multiplying to your x value, that's going to always create a horizontal compression. If the number that's multiplying to your x is between 0 and 1, that's going to create the stretch behavior, horizontal stretch. And then our last graph that we want to generate is what happens when my x gets a negative sign or a -1 multiplier on it. Well, that is going to change some things, and that's why we have these -4, -2, -1 values, because, for instance, with -4, if I put that in for x, I'd get minus the negative 4. That would change into a positive 4 that I can square root and get a value of 2. Negative 2, I could do the same thing. I could do minus negative 2 becomes a positive 2. That one, we can't really simplify. It's just square root of 2. And we found that earlier. That was 1.4. For negative 1, the two negatives go into a positive square root of 1. The square root of 1 is 1. And at 0, the negative 0 really just stays 0. When you square root that value of 0, you get 0 again. And then interestingly, when I plug in 1, now I have those negative values, right? I have a negative 1 underneath my square root. And so that's when these guys are not points we can graph. These are not real points. So same problem with 4. When I put in 4, I get the square root of negative 4. So what would that look like on my graph? Well, when x is negative 4, I'd be at 2. I could graph the negative 2 point, but we don't really need it because I have the negative 1 point. And 0, 0. So we can see it has the same shape as the parent function, right? And same kind of key values. However, instead of being on the right side of my y-axis, now it's on the left side of my y-axis. And so this is going to be a reflection over the y-axis when you have that negative multiplier. So to summarize, when you have a horizontal stretch or compression, it's when your x is being replaced with some constant multiplier, 2x, right? That's what we're representing as our a value. If a is a value bigger than 1, for instance, our value that we used previously, that was bigger than 1 was 3. When that happens, you're going to have the horizontal compression by 1 divided by whatever number you see, right? So in this instance, it was 1 divided by my a value of 3. If your value of a, or your multiplier to x, is between 0 and 1, for instance, for our h of x function, it was 1/2, that's going to create a horizontal stretch by 1 over whatever that value is. So 1 over 1/2 got me the stretch value of 2. And if my x value has a negative multiplier, then that's going to be a reflection, and we saw that that reflection was over the y-axis. And that's all of my transformations. So we took all of our transformations kind of one at a time, but in reality you could have many of them combining together. So let's run through our list. What are all the things that we can do to a graph? Well, I can shift it up and down vertically, right? How do we do that? If I add a number outside my parent function, that will move it up. If I subtract a number, that will move it down, right? I can also move my graph horizontally, left or right. This is the part where it's counterintuitive. So if I add a number, that's actually going to move it to the left. When I subtract a number, that will move it to the right. I can also make vertical changes, so I can vertically stretch or compress my graph, or change my y values to negative y values, creating that x-axis reflection. And those are all driven by multiplying a constant number outside your parent function. I could also include a multiplier inside my parent function where x is, and that would create horizontal stretching and compression, and would also make my graph reflect over the y-axis. So that's all of our transformations. So we just want to be aware of what all those things do. If we see a number affecting our parent function in one of those ways, characterizing what that's going to do to our graph. And we'll see later on all of our parent functions coming together, all of our transformations coming together, and so we can see if we do multiple transformations, how we can account for each one.